When working with forces, the most useful diagram we can make is a Freebody diagram. The Freebody diagram is a vector diagram that shows how the forces act on an object. There are two ways that we typically draw a Freebody diagram. The first is called an extended Freebody diagram. In an extended Freebody diagram, I simply draw the forces on top of a picture of the object so that it shows me each force and where it acts on the object. As we will see later in the course, an extended Freebody diagram is useful when dealing with rotational motion, since the torque exerted on an object depends not only on the force, but also on where the force acts on the object. The second diagram is a center of mass Freebody diagram. In this Freebody diagram, I represent the object as a point at its center of mass and draw all the forces as if they act at that point. For the first several weeks of the course, we will model objects as if they are point masses. As a result, we will draw Freebody diagrams from the center of mass. There is a series of questions that are helpful in terms of making sure we get the right Freebody diagram for a physics problem. Each question helps us determine whether a certain force needs to be included in our diagram. Let's walk through this set of questions and lay out what information we know about each force if it needs to be included. The first question is, does the object have mass? If the answer to that question is yes, then we know that we are going to draw a gravitational force in the Freebody diagram. For the first part of the course, we will only deal with the weight of an object at or near the surface of the Earth. Under these circumstances, we know that we can calculate the magnitude of the gravitational force as mass times the magnitude of the local gravitational acceleration. We also know that the gravitational force at or near the surface of the Earth is going to always point down. So if an object has mass, we're going to draw a gravitational force in the Freebody diagram that points straight down, and we have an equation we can use to calculate the magnitude of the gravitational force if the object's mass is known. The second question is the object in contact with the surface? If the answer is yes, then we know that we're going to have a normal component and that the normal component of the contact force will be perpendicular to the surface. Notice that there is not an equation for calculating the magnitude of the normal force. We will talk about what we do to calculate the magnitudes of forces that aren't given to us and we don't have an equation for. But for the moment, just recognize that there is no equation that we can automatically use to calculate the magnitude of the normal force. So if our object is in contact with the surface, we must have a normal force. Of course, we might also have a friction component. So the next question we will ask is there friction between the surface and the object? Some of the surfaces we'll deal with we'll talk about as being frictionless. So in that case, the answer to this question would be no. On the other hand, if we have a rough surface, then the answer to this question is yes, and we know that we need to draw in a friction force. To figure out what type of friction force we need, we will ask, is the object moving relative to the surface? If the object is sliding across the surface, then I know I'm going to have kinetic friction. If it's not sliding relative to the surface, then we need static friction. In terms of the magnitude of a friction force, I do have an equation that I can use to calculate the magnitude of kinetic friction and for the maximum value of static friction. In both cases, the magnitude of the friction force is given by multiplying the appropriate coefficient of friction times the magnitude of the normal. The fact that you can relate the magnitude of the normal to the magnitude of friction emphasizes the fact that these two forces are really just the perpendicular components of the force exerted on an object when it's in contact with the surface. It is worth remembering that static friction can have a magnitude from 0 all the way up to its maximum value, but the equation here can only tell me the maximum value. If the object isn't just about to start moving, you cannot use the equation to calculate the value of static friction. The last detail I need to figure out is what direction the friction force points. The most useful question to help figure out the direction of friction is which way does the object move or want to move. In the same way that I know the normal component always points perpendicular to the surface, friction will always point along the surface. If the friction force acting on the object is kinetic friction, the kinetic friction will always oppose the relative motion of the object as it slides across the surface. It can often be more difficult to determine the direction of static friction, but it is generally useful to think about how the object would move if the surface was frictionless. Static friction will oppose the motion that the object would have undergone if the surface was frictionless. The next question is there a rope or anything else that acts like a rope that is pulling on the object? If the answer is yes, then there is a tension force acting on the object, and we know that it will be directed along the rope. Like with the normal, we do not have a special equation that we can use to calculate the magnitude of the tension force. And finally, the last question that we will ask is there anything else exerting a force on the object? If something else is pushing on the object that we haven't already dealt with, then we need to include an applied force. Typically, you will be told the direction that anything else pushes on an object, so you will know which way the applied force points. To see how these questions work, let's look at two examples. For the first example, I've got a box of mass M initially at rest as it slides to the right across a rough horizontal table as it is pushed by a force angled 30 degrees below the horizontal. Because we will spend so much of the time in this course focused on how systems evolve, I'm going to go ahead and draw two pictures. One for the box as it is initially at rest, and the second for the box as it is moving after I have pushed it a small distance across the table. You will notice that both pictures are very similar. In both cases, I have a force pushing on the box that points in the direction 30 degrees below the horizontal. To draw the Freebody diagram, let's walk through our series of questions. Question 1, does the box have mass? The answer is yes. We're told it's a box of mass M, so I need to draw in a gravitational force that points downward. Question 2, is the box in contact with the surface? The answer is yes, it's in contact with a horizontal table, so there must be a normal force acting on the box that keeps it from falling. Because the table is horizontal, the normal force must act vertically. In this case, because the box sits on the table pushes up on the box. Question 3, do I need friction? In this case, yes, because I'm told that my table is rough. To determine what type of friction acts on the box, I need to ask whether or not the box is moving relative to the surface. It is moving relative to the table as it slides to the right, so I know that I'm going to need kinetic friction. In which direction is the box moving? It moves to the right, so the force of kinetic friction will oppose that motion and point back to the left. Question 4, is there a rope or a string or a chain or a cable or anything that acts like that pulling on the box? In this case, there isn't, so I don't have to worry about a tension force. Our last question, is there anything else pushing on the box? There's a force pushing on the box at a 30 degree angle below the horizontal. We will treat this force as an applied force and draw it in the Freebody diagram at an angle of 30 degrees below the horizontal. So here's the correct Freebody diagram for the box. Let's look at one more example. In this case, I also have a box of mass M, but now it is resting on a frictionless plane. The plane is inclined at a 30 degree angle above the horizontal, and a rope that runs parallel to the plane is connected to the box and tied off to a wall at the top of the plane. In this example, the box is just sitting there, so my initial and final pictures for the system are exactly the same. To set up the Freebody diagram, I'll run through my series of questions again. Does the box have mass? Yes. So I need to draw in a gravitational force that's going to point down. Is the box in contact with the surface? Yes, it's in contact with the plane, so there will be a normal force in the Freebody diagram. Because the plane isn't horizontal and the normal still needs to be perpendicular to the plane, the normal force must point up and to the right. By tilting the plane 30 degrees from the horizontal, the normal has been tilted by that same 30 degree angle from the vertical. Do I need friction? In this case, the answer is no, because I'm told in the problem that the plane is frictionless. Is there a rope or a string or a chain or a cable pulling on the box? In this case, there is. I've got a rope that runs parallel to the plane that holds the box in place. Because the plane makes a 30 degree angle with the horizontal, the rope must also pull the box at a 30 degree angle above the horizontal. Are there any forces pushing on the box? All the forces needed to hold the box in place have already been taken care of, so there are no applied forces acting on the box. This then is the Freebody diagram for the box in this example.